Good day, everybody. This is Chris with the Ancient Scholar. I hope this video finds you all doing well given contemporary situations and circumstances. So what I'd like to talk about today is chloroquine and hydroxychloroquine, and specifically how these might be utilized as a novel treatment for COVID-19, or rather for combating the effects of the SARS-CoV-2 virus. So let's just go ahead and jump right in and talk about what chloroquine and hydroxychloroquine are. So chloroquine and its cousin hydroxychloroquine is a very well-known molecule. It was actually developed in the 1940s, or discovered in the 1940s, and it was initially used as a medication to treat malaria. It was an anti-malarial medication, and we won't really talk about its mechanism of action as an anti-malarial because unfortunately, malaria is very good at becoming resistant to the effects of chloroquine and hydroxychloroquine. So chloroquine has largely fallen out of favor as a treatment for malaria due to the high degree of resistance of the various malarial parasites. However, chloroquine does have some other actions associated with it. So if we take a look at chloroquine molecule, I have the chloroquine molecule here, and you can see that the chloroquine molecule has a benzene ring with a chlorine attached to it, and then that benzene ring is bonded to a pyridine ring, which has a nitrogen down here, and then you've got a nitrogen here as well. You've got a little carbon bridge with some methyl groups, and then at the end here you have a tertiary amine group. And if I were to replace this methyl group here with a hydroxyl group or an alcohol group, or OH, that would make this chloroquine molecule hydroxychloroquine. So that's really the only modification that we make, and essentially the mechanism of action is going to be the same with chloroquine and hydroxychloroquine. However, hydroxychloroquine does have a slightly better safety profile. Therefore, I think it's probably going to be the preferred medication if, in fact, it is shown that there is any efficacy to be found with these medications. Okay, so I think the next question is, well, how might chloroquine, or rather hydroxychloroquine, act as an antiviral or effective antiviral therapy? Well, it really comes down to two major mechanisms. So the two major mechanisms are going to be, first and foremost, the molecule, chloroquine or hydroxychloroquine, is it's going to have action on something called the endosome or the endolysosome. So it'll act on the endosome or perhaps the endolysosome. And then the other area where hydroxychloroquine may work is it actually functions as something called a zinc ionophore. A zinc ionophore. So those are the two primary mechanisms of action that we hypothesize. So let's go ahead and break these down. So the first mechanism I want to talk about is how it may act on the endosome or the endolysosome. So here on the right, I have the coronavirus. So I have the SARS-CoV-2 virus. And remember that the SARS-CoV-2 virus is covered, or the envelope of the virus is covered in these spike proteins right here. And the spike proteins can bind to the ACE2 receptor, the angiotensin converting enzyme 2 receptor of cells, particularly talking about SARS-CoV-2. These are going to be cells in both the upper and lower respiratory tracts. So these will be the ciliated columnar epithelial cells and the type 2 alveolar pneumocytes, which are the surfactant producing cells in the lower peripheral areas of the lungs. And what happens is once that virus binds to the ACE2 inhibitor, the virus can then merge into the target cell, be it a type 2 alveolar pneumocyte or a pseudo-stratified columnar epithelial cell of the upper or perhaps the lower respiratory tract. Essentially, because the envelope is a lipid layer, a lipid membrane, which is essentially the same as the phospholipid bilayer that we see in eukaryotic cells within our body. Following attachment, the virus that can then fuse, it will fuse into the cell membrane. And then when it fuses into the cell membrane, there will be a piece of cell membrane that then surrounds the virus. That's my clock going off. That's a loon clock. Sorry about hearing that sound in the background, but that's just the way it goes. It's kind of late at night here at home as I'm working on these videos. All right, so following fusion, the virus then gets surrounded by a piece of the lipid bilayer of the cell itself. And this structure, this new structure that's produced, is something called an endosome. All right, so you have the endosome following fusion of the virus. So the virus is inside of that endosome. And then you have these little structures within the cytoplasm of the cell, and these little structures are known as lysosomes. And these lysosomes are little membrane-bound containers, little containers that contain enzymes within them. And the specific enzyme that we are most concerned about is something called a protease enzyme. So these contain protease. These contain protease enzymes. And protease enzymes are enzymes that catalyze the breakdown of proteins. And so what's going to happen is these protease enzymes will migrate to the endosome and attach to the endosome and create a new structure known as an endolysosome. As an endolysosome. So the lysosomes will attach and form a new structure called an endolysosome. And then what happens is those little protease enzymes can get released, and the release of the protease enzymes then interacts with proteins, the spike proteins, on the SARS-CoV-2 virus, and then that allows the virus to release the RNA within it. And then that RNA, that single-stranded RNA template that was stored inside of the virus, gets released due to those protease enzymes from the lysosomes that have attached to the endosome to form an endolysosome. And then what happens is the single-stranded RNA, following release of the single-stranded RNA, that single-stranded RNA, that template, then gets copied, or it gets replicated rather. So that template gets released and then it gets replicated into proper messenger RNA, and then the messenger RNA can then get read by ribosomes within the cell and get turned into viruses. That's the actual code. Now, in order for that single-stranded RNA template to be replicated, there is a very important enzyme that catalyzes a very important step of this replication. So I'll draw that here. All right, so following the release of the single-stranded RNA template, replication occurs, and there's an enzyme, and that enzyme is known as RNA dependent RNA dependent, or rather it's known as viral RNA dependent RNA polymerase. And a polymer, so anything that ends with ASE is going to be an enzyme, and enzymes are typically proteins. So proteases are enzymes that help break proteins down. Polymerases, a polymer is just a string of molecules bound together. So you have a long string of molecules bound together like that. You call that a polymer, right? So this helps bind things together, specifically RNA. All right, so this is RNA-dependent or viral RNA-dependent RNA polymerase, and this is sometimes just shortened to RD, RP. All right, RNA-dependent RNA polymerase. All right, and again, so let's just review this real quickly again. So the SARS-CoV-2 virus attaches to the ACE2 receptor. It then fuses with the cell membrane following attachment. That forms an endosome within the cell itself. Lysosomes within the cell attach to the endosome to form something called an endolysosome, and then protease enzymes within those lysosomes allow the RNA to be released from the virus, and along with that RNA release, there is a protein inside of that virus called RNA-dependent RNA polymerase, which catalyzes the conversion of the RNA template into proper messenger RNA. All right, so that's the kind of the high-yield version of what's going on there. Okay, so now let's talk about chloroquine. So where does chloroquine come into play? Well, the first area that chloroquine comes into play is over here, and I have chloroquine or hydroxychloroquine inside of a box called CHL. That's just shorthand for the chloroquine. All right, and chloroquine, if we look at its pKa value, and if you want to know what pKa is, I've actually got several videos on acid-base physiology, and you can reference those. But essentially, pKa is a logarithmic. You take a logarithmic negative log of something called the Ka, and the Ka is the dissociation constant. So essentially, anything that can act as an acid or a base, when you put it in water, will convert into an acid or a base at a certain rate, and that's called the dissociation constant, and then you can take the log of it to get something called the pKa. All we really have to know is that the smaller the pKa value is for something, the more acidic, okay, the more acid-like it is, right? So if we look at the pKa of chloroquine, it has a pKa of 8.5, which is actually fairly large. So that actually makes chloroquine a weak base. And so what happens is, because chloroquine is a weak base, it tends to accept hydrogen ions. That's what makes a base a base. These are also known as protons. So it tends to protonate when it gets into the body, into the cells. And specifically what chloroquine tends to do, and it's not entirely clear where this happens, but it seems to either in the endolysosome or in the endosome, it will enter, the chloroquine will enter the endosome or the endolysosome. It will then protonate, and it'll become a base, and then it'll get trapped within those, within the endolysosomes or perhaps the endosomes. And the interesting thing is, in order for the RNA template to be released, the pH needs to be very low within the endolysosome. And it's approximately about 4.7. And I believe that it needs to be that low for RNA to be released. And just for reference, a pH of 7 is what we consider, 7.0 is what we consider neutral, whereas 14 is considered highly, highly basic, and then 0 is considered highly, highly acidic. So 4.7 is on the more acidic side of the pH. So when chloroquine gets in there, it protonates, it starts gobbling up the acids, the hydrogen ions or the protons, and then it pushes the pH up toward a more alkalotic range, and that prevents the release of the single-stranded RNA template. All right, so that's one area where it works. And the other area where chloroquine or hydroxychloroquine seems to work is over here on the left-hand side of the cell in the box. And it works by acting as something known as a zinc ionophore. And essentially what it does, again, we'll go for high-yield concepts here, is it facilitates entry of zinc ions into the cell. So that's the Zn plus there. So what it does is it facilitates the entry of zinc ions into the cell. And so what happens is as zinc ions enter the cell, zinc ions interact with the RNA, the viral RNA-dependent RNA polymerase, and it actually inhibits the RNA polymerase, so it prevents replication of the RNA template into messenger RNA. So chloroquine works on two fronts. It works by preventing the release of the RNA template, and it also seems to work by preventing the action of the viral RNA-dependent RNA polymerase enzyme. All right, so that's all well and good, but let's talk about some potential problems. Okay, so the next question is, now that we have a working hypothesis for how chloroquine and hydroxychloroquine may be helpful in the setting of COVID-19, is there any evidence supporting this hypothesis? Well, currently, the only available evidence is in the form of some anecdotal case reports. So these are individual providers that said, hey, I administered this drug by itself or in concert with other substances such as zithromycin, and the patients seemed to do okay. Purely anecdotal. It's hard to say whether or not there really was any effect there. There are a few published case studies or case reports without controls. So these are physicians that have written up, hey, I gave this medication to a series of 5 or 6 patients and they all seem to do okay. Maybe there's an effect here. Unfortunately, there were no controls in these cases, so it's hard to say whether or not there really was an effect or if this was just these patients naturally, their immune system naturally getting over COVID-19. There were really no controls in those case studies. So again, it's hard to say what kind of effect really may exist. However, there are controlled studies that are in progress as we speak, and that is to say that we are giving a control. So you have a group of patients that are not receiving the medication, and then you have a group of patients that are receiving the medication, and then we can actually compare the two groups and see what's going on. That really helps us tease out an actual effect. The evidence from those case studies has not been gathered at this point. It's forthcoming, so hopefully we will see something arise from these studies in the upcoming weeks and months. Now, with that in mind, we also have to think about side effects. And the side effects profile is rather concerning with chloroquine and hydroxychloroquine. Now, even though hydroxychloroquine is a little safer, there are substantial side effects, and these cannot be discounted. So common side effects associated with these drugs. There are common visual side effects. They can range from rather mild, like blurry vision, all the way up to rather severe side effects that include damage to the retina of the eye, or what we call retinopathy, and can cause severe loss of vision. You can have some hearing side effects. You can have tinnitus or ringing in the ears develop, all the way to serious hearing loss. There are some severe neurological side effects. Can include all sorts of types of altered mental status and cognitive changes, to rather strange dreams and even hallucinations in some cases. I actually, many years ago, I took a microbiology course from a PhD, and when she did her PhD work in Costa Rica, she was on chloroquine to prevent malaria, and she ended up having lots of concerning neurological side effects, hallucinations of snakes and things like that. She had a really hard time with it, and this is pretty common. These are pretty common side effects, unfortunately. There are some well-known cardiovascular side effects associated with chloroquine as well. Can range from AV, atrioventricular blocks. So these are blocks involving conduction from the SA to the AV node. It can be something as mild as, say, a first-degree AV block to more problematic, higher-grade second-degree and even complete heart blocks. Blocking of conduction through the bundle branches, or delay of conduction through the bundle branches, or what we call bundle branch blocks. Some patients can even go on to develop cardiomyopathies and congestive heart failure, actual heart failure. There are lots of hematological effects associated with chloroquine and hydroxychloroquine as well. They can range from anemia, so low hemoglobin hematocrit, thrombocytopenia. This is a loss or a low level of platelets. Neutropenia, these are low neutrophil count, which is a white blood cell. And these drugs are also well known to have immune suppressing effects. In fact, we typically see these drugs not used as anti-malarial drugs due to malaria resistance, but the common use for these drugs is actually to treat patients that have autoimmune disorders where their immune system is actually attacking its own body cells. So disorders such as systemic lupus erythematosus, SLE, or lupus, rheumatoid arthritis. These particular patients are actually sometimes put on these medications because the medications have an immune suppressing side effect. And then you can even have more mundane side effects, such as metallic taste in the mouth when you try to eat or drink anything, to gastrointestinal side effects, nausea, vomiting, diarrhea, and sometimes severe abdominal pain. So the side effects profile is pretty substantial. The therapeutic index for these drugs is fairly narrow, so the risk of toxicity can be elevated. In the setting of an overdose, these are not benign drugs to overdose on by any means. These patients can rapidly develop coma, respiratory arrest, and even cardiac arrest, and we have actually seen a few people die as a result of overdosing on chloroquine and hydroxychloroquine. I believe the most notable case in the United States is a husband and wife in Arizona that got a hold of a chloroquine derivative that was used to treat parasitic infections of fish, and they then consumed this chloroquine derivative and ended up overdosing inadvertently. I believe the husband died, and the wife is currently in critical condition. And I believe at least one other person has died in the United Kingdom as a result of overdosing on a chloroquine derivative. So the side effects profile is pretty substantial. And so what we're going to have to now juggle moving forward is, does the evidence, right, is there enough benefit to being on these drugs, right? Do the benefits outweigh the risks of serious side effects. And that's a very important question that we'll need to answer in the upcoming weeks and months. I don't currently have a good answer for that now, but it is definitely something that needs to be answered in the future. All right, I think I'm going to cut the video off here. Hopefully you all found this helpful, and hopefully you now understand the potential role for chloroquine derivatives in treating COVID-19. I'll see you all in the next video. Please take care.